Hello, so today we are going to do this problem, which is part of Leetcode weekly contest, this week's contest, and this is problem number 3. Maximum number that sum of the prices is less than or equal to k. So essentially we have two parameters here. We have k and we have x. And we consider s being the one indexed binary representation of a number. For that number, where is the concept of price? The price basically is the number of i's, so basically the number of indices in the binary representation starting from 1, where I is divisible by x, so x is this number that we get, but also the number at position I is set. Okay, so a price of any given number is basically the number of bits set in positions that are multiple of x. Okay, and what we want is to find the greatest integer such that the sum of all the prices from 1 up to that integer is less than or equal to k. Okay, so that's the idea here. Let's take a look at the first example. So k is equal to 9, so that means we are looking for a number where the sum of the prices is less than or equal to k, less than or equal to 9. Okay, and so if you try multiple examples, you'll find that that number is 6 because if we take the binary representation here from 1 to 6, okay, x is equal to 1, so that means basically every number is divisible by 1, right? So we can consider all bits that are set because this will always be true. And so in that case we have 1, 2, 3, 4, 5, 6, 7, 8, 9. So we have 9 set bits, which is exactly small or equal to k. If we go up to 7, we will have 7 binary representation is this, so we'd have 9 plus 3, so that's bigger than k. So that's why the largest one possible is 6, because if you go 7, 8, 9, you will only increase the number of bits. But we really understand that. So the problem says we need to find the greatest number, so largest number that such that the sum of the prices, okay, of, let's call it a, and a is from 1 to num, to that number, right, such that the sum of the prices here are smaller or equal to k. Now what's the definition of a price? Well, the definition is of a price of a is basically the sum of the, if we take the binary representation, it's going to be the count, okay, of I, of those, basically, say, I, which is the position in binary representation, okay, starting from 1, because it's 1 indexed, okay, and then what are the properties of I? Only if, we count it only if it's divisible by x, right, and in the binary representation, the value at I is equal to 1. It's set basically in the binary representation of A. Okay? So this is the rule. Okay, so what do we need to figure out here? We need to figure out an easy way to compute the price, a non-expensive way to compute the price. Because once we do, we can just get the sum, right? Get the sum and then check if it's small or equal to k. But then, of course, we need to figure out the second piece, which is how do we get the largest number, okay? And so first, let's think about how do we get this largest number, and then the second piece, we'll think about the price. Okay, so how do we get the largest number? Well, with largest, we know that k is up to 10 to the power of 15, so this is very large, and we said we need some sort of a log solution, and we need to think about binary search. And this is where binary search actually is useful, because with binary search, we can just look in the range and try all the numbers possible, and try all the numbers, and then find the largest one where some condition is true. What do I mean by that? So to apply binary search first, you need to have a monotonic function. And by monotonic function means you need to have false first, and then you need to start having true values. Okay? Or you need to have true values, and then you need to start having false values, but once it becomes false, it stays false, and once it becomes true, it stays true. So what we can look for here is we can look for numbers, right? We can keep looking for numbers where the sum of the price is smaller than ks, okay? And since prices increase, we saw that in the first example where once we reach it, the count is 9 with 6. If we add more numbers, the count of bit will only increase, right? And so this already tells you that the function is monotonically increasing, but in this format here. Basically, this is first true, right? Because let's say in the example that we saw in the first example where k equal to 9 and x equal to 1, for just number 1, it's true because the number of set bit is just 1. And then for 2, it's true because the number of set bits is just two, right? This is 1 plus 1, so it's just 2. The prices are just 2. With 3, it's because 3 is 1, 1. So the binary representation here is this, the binary representation here is this, so this is 2. And now for 1, the binary representation is 0, 1, 1, right? And so now we have 4. It's still smaller than k equal to 9. And we go all the way until 6, where the total is 9. And then when we check 7, now the total, because 11 is adds 3 bits, 9 plus 3, now it's 12. Okay, now we start false. And now as we increment, this sum will only increase and it will stay false. Okay, so now we already know that this function here is monotonic function. And so we can apply binary search. Okay, so that's the first part on why we can apply binary search. Now binary search, we just need to find the bounds, and then we can do just our implementation of binary search. But after that, we need to figure out how to actually implement this. But first, let's figure out our bounds. So what's the bounds for binary search, at least like the format that I usually solve with, is we need to choose bounds that are outside where it can never be true. So for low, let's just choose 0, because then we would have 0-bit set, and in that case, it's always guaranteed to be smaller than k, because k is at least bigger or equal to 1. Okay, so we choose 0 for low. Now what do we choose for high? Well, we know k is up to 10 to the power of 15. And that's what we are looking for. And we know the number of set bits that you could have. Well, if we choose the number, because this is going to look for the price is the number of set bits. So let's just try with all the bits set, so 64 bits multiplied by 10 to the power of 15, and then we add 1 just to be outside of the bounds, okay? I do think you can still try with 10 to the power of 15 and see if it works, but just to be safe, we'll just do it like if all the bits were set. And then we'll just do our binary search and find the answer. Basically, we'll maintain low to be true, we'll maintain high to be false, and then we'll stop when the difference is just 1, and we'll return low. Okay? Okay, so now what's remaining is how do we compute this price function here? This part here, how do we compute it? That's where the binary observation comes in. So remember, the problem says we want to index the bits 1 indexed. So that means this index 1, 2, 3, 4. And here, this is just the binary representation of 0. This is the binary representation of 1. This is the binary representation of 2. And this is the binary representation of 3 all the way down until 15, okay? So let's see how we can just get some formula going here. So the first thing you will notice, if you look at this, is that, for example, here we have 0, and then we have 1. And then we have 0, and then we have 1. So if we call these, for example, like rows, and then we alternate between 0 and 1 every one row. So every next one row we alternate. Right? So we have 1 here, and then we have 0 here, 0 here. Right? And now if we take a look at the second one, the second column for all the numbers, well, we have 2 zeros, and then we alternate and have 2 ones. 2 ones, 2 ones, and then we have here 2 zeros, 2 zeros. So you can see it's alternating. First 2 zeros, then 2 ones, then 2 zeros, then 2 ones, 2 zeros, 2 ones. And the same pattern follows, but every time the number is larger. The number where we toggle between 0 and 1 is larger. So for example, here we have 4 zeros, and then we get 4 ones. And then we have another 4 zeros, and then we have 4 ones. Right? You get the idea. And then the next one is we have 4, 5, 6, 7, 8 zeros, and then we alternate to 8 ones. If you draw more examples, you'll see that it continues after. Okay? So that's what we notice here. Now, what are the size of each? So here we have 1. The size of the times we alternate is just 2 to the power of 0 for this one. And the size here is 2 to the power of 1. The size here is 2 to the power of 2. The size here is 2 to the power of 3, because the group size here is 8, so 2 to the power of 3. Here is 4, so it's 2 to the power of 4. Here it's 2 to the power of 1, right? And so already you know the groups in which, at each of which we alternate after, those are 2 to the power of the number minus 1, okay? But another observation is that, another way to observe this is that if you look at the groups, and by groups I mean the 0 and the zeros or ones, and then we have the same group again. So let's look, for example, at this here. So you can see we have 0, 0, and then 1, 1. So 2 zeros, 2 ones, and then we have the same group afterwards. 2 zeros, 2 ones, and then 2 zeros, 2 ones. And the same pattern applies here. We have 4 zeros, 4 ones. And then after that, we have another 4 zeros, 4 ones. Okay? So we have sort of groups that have the same number of zeros and the same number of ones. Same thing here. We have it of size 2. Right? Okay, so now knowing this, how can this help us? Well, what are we looking for? We are looking for basically the number of set bits in each of these, in the total of all these numbers. So for example, we know up to 4, let's say up to 3 here. If we are considering num equal to 3, how do we count the number of set bits? Well, it's easy. We know that each group here, the first group we know it has 2 ones. The second group we know it has 2 ones. The third group we know it has 0 ones up to 3, and the fourth one it has 0 ones. Okay, and as we go, so we know basically here that we just need to count 2 plus 2 to get 4. Okay, so that's how it will help us, because it's easy to identify for up to that number for each group how many ones are there. But how do we sort of convert this into like a concrete formula here? How do we find the number of ones in a group? I'll list what we need to find. And how do we find the number of groups? Okay. So if we find the number of groups and the number of ones in a group, so with these two, we'll know the number of ones if we have full groups, right? But then there is a problem remaining, because we don't always have a full group. Like in this case for 3, we had a full group because it had a full group for index I and index 2 because it ends here. But we don't have a full group for index 3 because we don't have all the 4 ones, right? The group did not end yet. And so for index 3, we need to find how many ones are just in this portion. Just in this portion here, right? Okay. Now, even if we take a look, for example, at 4, let's say if we take a look at 4 here, now let's see, where do we have groups? We have full groups for these two, but then for this is for index 1. We don't have a full group here. We have to find how many ones in just this portion, just the what's covered in 4 here, right? Same thing for this part here. For 4, we have this group, but this one we only have one position. For this group, we don't have a full group. We only have up to here. And so we need to find how many ones we have in this here, and we have just one. So with just these two, we can multiply. If we get the number of full groups we have, we can multiply with the number of ones in group, and that will help us find the number of ones. But if we don't have a full group, we'll have to find a way to find the remainder. Now, how do we do that? So let's think about that. So to find the remainder, well, what do we need? Well, we need to know how many just positions are remaining. So how do we do that? Well, we do that by just doing the number itself modulo the group size. Why is that? Because remember, group size, for example, here is 2 in this first index I equal to 1. So how do we find for 4 how many we have? Well, we just take 4, okay, modulo the group size, modulo the group size. Now, of course, here for 4 we need to increment by 1, so we need to increment by 1 because we start counting from 0. And so how many we have, if we take the number plus 1, how many we have modulo the group size. So how many? 1, we add 1 for this 0. And so that's 5 modulo group size of 2. That means we have 1 remainder, right? Same thing for this group. How many we have? 4 plus 1 for this 0. So in that case, we have, so of course, remember, that means initially in our function, we need to increment by 1 for this 0 here, okay? Just something to keep in mind. But here, for example, for group index 2, we will say, okay, 5 modulo 4. So that will give us 1, and that's true because we have only this one. Now, what about this index 3? Well, 5 modulo the group size, which in this case is 8. So that's 5. Okay, so that's the idea of how we find the remainder. Okay, so this is how we find the remainder, but we don't just want to find the remainder, we want to find how many ones are in the remainder. So for example, if we go back here, for index 1 here, we have 0 in the remainder, 0 ones set bit in the remainder. Here we have 0 ones in the remainder, but here we have 1 bit set in the remainder. Here we have 0 bit set in the remainder. So how do we find that? Okay, so to find the number of for the remainder, to find the number of ones, what we can do is just take the full remainder here, so, and we need to subtract just the number of zeros, okay, in that remainder, right? Then, sorry, the number of zeros in a group. Why is that? Because we know with the alternating here, we know zeros appear first and then 1 appears. And so to know the number of, we know this is not a full group, so we won't have all the ones. And so we just need to know how many zeros, okay, are in the group, right? And then if the remainder is larger than the number of zeros, that means whatever is the difference, that's what we have remaining. That's the number of ones we have. Right? If the number of zeros is bigger than the remainder, so that's maybe because, for example, in this case we have, in this case where we have 2 zeros, but the remainder is just 1, in that case, that means we have no ones because we haven't even finished the zeros portion. And so that's why we take the max of 0 in this. And this will give us the number of ones in the remainder. Okay? And now, to find the number of set bits, it's really easy. We can just take number of set bits for a specific index, I. We can just take this multiplied by this. So this will give us the number of ones in the full groups. So the ones in a group multiplied by the number of groups, number of full groups, let's call them, plus the number of ones in the remainder. Okay, and that we can add this for every, how many times should we add this? Well, we should add it for every I that is divisible by X, right? Because remember, the condition is bit is set, the count of set bit that are divisible by X. And so how do we do that? So we know that part of our formula is this, but we only want the numbers, the positions, I's from here that are divisible by X. So how do we do that? Well, let's actually just do a for loop for I in the range of, we know we want to start from X because divisors of X are just X, 2X, 3X, 4X, all the way until the end, right? Those are the divisors of X. Anything below X is not a divisor, so no need to look. And so we need to find our upper bound, but we know our increment is going to be X. Each time we add an X, we add an X. So for example, if X is divisible by, is equal to 2, we need to just look at 2, 4, 6, 8, and all the way up, right? Now what's the limit here? Well, this is binary, right? Okay, so this is binary. So this tells you that we would have to stop at 64 bits, right? And so we have to stop at 64. But here X may be, we don't know, X may be 1, maybe 0, maybe 2. So let's just stop at 64 plus X. Okay, and this is, and we do this formula here for every I that in this range. And we do the formula here to just calculate the number of set bits, and then we check if the total, so this is enough to calculate the price. Now we just check if it's smaller or equal to K in our binary search solution. Full code here, but I will first explain the binary search solution, and then we can after that explain the price. So we said binary search, we just need to go through the range. Now in the overview I said, just to be safe, we'll do all the binary count multiplied by the upper bound for K, and then plus by 1 just to be outside of the bound, and for low 0 because K can never is always bigger than 0. And so we do just normal binary search. We stop when we have it like this. So we stop when we are at the last true for low and the first false. And so basically when the difference between both is smaller or equal to 1. Okay. F of low will always be true in this case. F of high of the function price here, this function, which is what I call f of x, f of high will always be false. Okay, so we do this binary search, just basic template implementation, but here we check if the price is smaller or equal to K. So this is basically the sum of the prices from 1 to mid. Okay, so if it's smaller than or equal to K, that means we are at a true. So we don't know if we are at the last true or the middle true or the first true. We don't know which true position, and so we just keep low at that position because it may be the last one, but it also may be something here, we don't know, and so we keep low at mid, right? But if it's a false, again, same logic, we don't know if this is the one of the further away false or the first false or the one before that, and so we just keep high at this position and maintain our invariant that f of low is always true and f of high is always false. Okay, and then at the end we return low because that's the, according to this condition, that means low is here and high is here, so we are at the last true. Okay, which means we are at the biggest number where the price, the sum of price is smaller or equal to K, right? So now let's see the implementation of price. So first we increment by 1. Remember, this is when I showed in the overview because we include 0 in the binary. In our binary representation, we increment 1 here. And then we just go x multiples of x because we only want to consider the bits position that are divisible by x, where I modulo x is equal to 0, right? And so here what I do is we get the number of ones in a group. Now remember, this is just 2 to the power of I minus 1 because remember for position 1, the number of zeros in a group was just 0 and 1. And so let me actually just write this down. So for index 1, the group format we had 0, 1, 0, 1. So a group had just 1, 0 and 1, 1. And that basically is represented by just 2 to the power of 0. And if we take a look at index 2, we had 0, 0, 2 zeros, and then 2 ones afterwards. And that's represented just by 2 to the power of 2 minus 1. This is I, which is 2 minus 1. So I minus 1 was 1, 2 to the power of 1, which is 2. And this pattern applies to all of them. And so the number of ones in each of these group, if you take a look, is just 2 to the power of I minus 1. And in binary, we can calculate it like this. Now, we know that in each group, we have equal number of zeros and ones. And so the number of ones is the same as the number of zeros. And so we just do the same calculation, 2 to the power of I minus 1 for each. Okay? Okay, so what's the group size? We said that the group size for 1 is 2, which is 2 to the power of I. And for I equal to 2, it's 4, which is 2 to the power of 2. And for I equal to 3, the size was 8. So we had like this, 1, 1, 1, like this. And so the size here was 8. And so each time it's just 2 to the power of I. And so that's what we have here, the group size. Not full group, okay. Now, one thing to, and we said the number of set bits is just the number of ones in the full groups plus the number of ones in the remainder, right? In the remainder. So now, to calculate the number of ones in the full groups, we just need to calculate the number of full groups. Let's call these full groups. And then we multiply it by the number of ones in a single group. That will give us the number of ones in the full groups. How do we find the full groups? It's just the number divided by the size of the group, which is just the number of zeros and the number of ones. And so that's what we do here. You could also just divide this by group size, which would be the same thing. Okay? And that now for the remainder, well, the number of remainders is just basically the entire remainder minus the zeros, because you only have zeros and ones, and that's what we saw in the overview, and so that's what we have here. Now, we max with 0 because what if the remainder is small, so it's less than the number of zeros in a group. In that case, that means there is no set bits, and so we just maximize with 0 to get 0, okay? And we do this for all the eligible I positions, and then we return this, which would be the sum of the prices, okay? So this is clever because it doesn't calculate the price for each number from 1 to a num. It actually calculates it 1 bit position at a time. But when we add up the number of set bits for each bit position, that's for each eligible bit position, that just would be equivalent to getting it number by number, right? And yeah, that's pretty much it. So this is calculating the price, which is the sum of the prices from 1 to num. And then this is just binary searches to find the greatest one that is small or equal to k. And that's exactly what we are asked, okay? So let's run this, and we can submit. And this gets accepted, okay? Thanks for watching, and see you on the next one.